Hello everybody, here we are, 7.2 scale diagrams and reductions. Previously we did 7.1 scale diagrams and enlargements. So this is kind of the reverse of that. I wrote out the notes for you so you don't have to read my printing. So our first note, scale factor can be written as whole numbers, fractions, decimals, and ratios. So could, for example, look something like this: 4 whole number. The fraction, here we have in our first example 1 over 200. As a decimal, you might see something like, 3.2. And as a ratio, maybe something like 1 to 40 or something like that. And our second note, when a scale factor is less than 1, the scale diagram will be smaller than the original, so it will be a reduction. So previously, all of our examples in 7.1, the scale factor was greater than 1, and so the scale diagram was bigger. But now here we are, less than 1, the scale diagram will be smaller. So I'll give you a second to write that down. Press pause now. And then let's move on. So number 1, a rectangular playground has the dimensions 24 by 16 meters. Draw a scale diagram of this playground with a scale factor of 1 to 200. So I'm going to draw our original, which will already be a scale diagram because obviously this isn't 24 meters by 16 meters. But let's live in a fantasy for a little bit. And there's a few equations that I might like us to write down, because we'll recall from our last notes that the scale factor equals the length of the scale diagram over the length of the original. And then it's also true that our original times our scale factor equals the scale diagram. And that's the one that we're going to use for this question right here, this piece of information, that the original times the scale factor is going to equal our scale diagram. It would also be good to write down this equation right here, that the scale factor equals the length of the scale diagram over the length of the original. So let's use this one right here. So we have the original. Let's use blue. We have the original, so 24 meters. We're going to times it by our scale factor, 1 over 200. And we'll get 24 over 200. And I'm going to make this into a decimal. I'll show you why. So let's go 24 divided by 200. And we get 0.12 meters. And the reason I want this as a decimal, if we have 0.12 meters, it'd be nice to have this in something that's a little bit easier to kind of conceive of. And I'm going to change this now. I'm going to times it by 100 to get this into centimeters. 12 centimeters. Okay, and then let's do our next one. Let's do the other side. We've got a 16 meter side times 1 over 200. We're going to get 16 over 200. And as a decimal, we will have 0.08 meters. I also want to times this by 100 to get us 8 centimeters. And now our scale diagram is going to look something like this. So 12 centimeters, that was our original length, and then this 8 centimeters, now our side. So there you go. One was in meters, one was in centimeters. You can see that it is now 1/200th of the size. So let's do the next one. A reduction of an object is to be drawn with a given scale factor. Determine the corresponding length in centimeters on the scale diagram. So let's see the corresponding length in centimeters. Yes, this section does require some converting between units. So good to remember how to convert between those. You can look it up if you need to, but good to know that a kilometer equals 1,000 meters, and that 1 meter equals 100 centimeters. That works like that. So for our first one, the reduction of an object is to be drawn with a given scale factor. Recall from up here that the original times scale factor equals our scale diagram. So original times scale factor equals our scale diagram. So fishing rod is length 280 centimeters and a scale factor of 1/50. So let's do those two. Let's do our original 280 times 1/50. Let's get 280 divided by just 50. That equals 280 divided by 50. There we go. 5.6 centimeters. So what was 280 centimeters? We multiplied it by the scale factor less than 1 of 1/50, and our new length is 5.6 centimeters. So that's just this equation over here. Our original times the scale factor equals our scale diagram. Let's do the next one. A boogie board is 1.5 meters, okay, and a scale factor of 0.05. So let's do, remember our answer needs to be in centimeters. So we could either kind of do this at either stage. We can go 1.5 and times that by 100 to get us to centimeters, 150 centimeters. And now we can multiply that by our scale factor. So 150 times 0.05, that's right? Yeah, 0.05 equals 7.5 centimeters. So our, what was originally 1.5 meters, multiplied by a scale factor of 0.05, our, length of our diagram is 7.5 centimeters. And our last one, we're doing a good amount of converting here. So a jogging route is 10 kilometers and the scale factor is 0.00002. Our answer needs to be in centimeters, as you'll recall. So we can do our 10 times. This is kind of the other method. We could do our conversion later in the question. Times 0.000, how many got here? 3 4 zeros, 2. And let's see what we get. 10 times 0.00002. Okay, we get 0.030, 0.0002, and that's kilometers. But now to get our answer to kilometers, we need to convert to centimeters. So first, let's times by 1,000. That's going to take us to meters. So times 1,000. So 0.2 meters. And then maybe I should do this in another color. Maybe I should have done that from the beginning. Let's do that. So we times by 1,000 to get us to meters. Now we're going to times by 100 to get us to centimeters. And so 0.2 times 100, it's going to give us 0.2 times 100, give us 20 centimeters. Okay, so those are those. And our last question, the scale diagram below has a scale factor of 0.25. What are the dimensions of the actual rectangle? Okay, so now we have another kind of iteration of our equation. Remember, it's true that the original times the scale factor equals the scale diagram. So now we have the scale factor, we have the scale diagram, and we want the original. So to get the original on its own in our equation, let's isolate the O. So let's divide each side by the scale factor. So what we do to one side, we're going to do to the other. And remember, this will cancel this out. This now, scale factor, anything divided by itself is 1. So we are left with, as another version of the equation, that the original equals the scale diagram divided by the scale factor. Okay, so that's a good one to have as well. So let's see. The scale diagram below has a scale factor of 0.25. What are the dimensions of the actual rectangle? Okay. Let me pause for a second here. Okay, everybody, I'm back. What gave me pause there is I realized I didn't have what are the dimensions of the scale diagram. So I've added that. I've referred to my notes. I've added it. The scale diagram below, so that I think means that your notes won't have it on there either. So can you please write 12 centimeters on the bottom here and 3 centimeters on the side? So now the scale diagram below is the scale factor. I mean, it always has the scale factor of 0.25. What are the dimensions of the actual rectangle? So now we know the dimensions of our scale diagram. We can figure out the original. So we have, let's do our scale diagram divided by our scale factor. So let's do our first one, 12 divided by our scale factor, 0.25 equals, let's use our calculator for this. 12 divided by 0.25 equals 48 centimeters. And our other side, 3 divided by 0.25 equals, 3 divided by 0.25 equals 12 centimeters. And so our actual rectangle would look something like, well, still, it's not going to be the real thing, but something like this. 12 centimeters by 48 centimeters. Okay, that works. Thank you so much. I'll let you know what textbook questions I'd like you to do.